Hello everyone, welcome to Drawing Hub. This is Sanjana, and in this video we'll be continuing with part 6 of Distributed Computing Module 1. In the previous sessions, we have already discussed about the basics of distributed system, relation to computer system components, motivation, features of distributed computing, primitives for distributed communication, and the different versions of send primitive, design issues, challenges, and applications. In this video, we'll be continuing with model of distributed computation. So let's get started. If you want to know more about those previous sessions, please watch my previous videos to get more clarification on those topics. Now, why do we need a computation model? Imagine you're watching a football match. You want to answer questions like which goal happened first, which pass caused the goal, were two players acting at the same time. Without a replay, it is difficult. Similarly, in a distributed system, many computers execute simultaneously. We need a way to describe what happened, where it happened, and in what order. That description is called the model of distributed computation. Distributed program. It is actually a program whose execution is divided among multiple processes running on different computers that communicate through messages. You don't have to think so much about it. Let's make it simple. Instead of one computer doing one program, we have computer A, which will be doing process P1, computer B will be doing process P2, computer C will be doing process P3, and all these processes together form one distributed program. Let's make it even simple. Think about Google search. When you search distributed computing, many servers will participate in that. One server will receive the request, another one will search the index, another one will rank the web pages, and another server will be displaying the result. We have discussed this multiple times in the previous sessions. And together, all these servers, they execute one distributed program. You should always remember each process has its own memory, it executes independently and communicates through messages. No process can directly access another process's memory. That is something you need to keep in mind. That is distributed programming. Then comes model of distributed execution. Model of distributed execution. Now suppose our distributed program starts running. What do we call its execution? Distributed execution. Yes, it is being executed. So a distributed execution is the execution of all the processes of a distributed program together, which includes the communication among them. Suppose there are three computers calculating weather data. Their computer A will collect temperature, computer B will calculate rainfall, computer C will predict tomorrow's weather. Together, this running activity is called, it is being executed, it's working over there. That's why it is distributed execution. So, distributed program means it is the code. The distributed program is the code and distributed execution is the running of that code. Okay, just like we have program, a C program, that is a code, and when we execute it, we get the result, just like that. Okay, then events. Events, everything that happens during an execution is called an event. Everything that happens during an execution is what we call events. Here you can see there are three events. Let's take an example. Imagine there is a process P1. Many things can happen, like receive message, will calculate it, send message, finish. Here, receiving the message is an event. Calculation, that is an event. Sending the message is an event. And three types are there, as you can see: internal events, message send events, message receive events. Internal event means it occurs only inside the process. There is no communication. Example, x equal to x plus 1, or sorting an array. That is internal event. It happens inside the process. Send event is a process sends a message, say there is a process P1, it will send a message called hello to the network, that is send event, sending a message. So what will be receive event? Here another process will receive the message. So from the network, that hello message will be received to P2. So send event, receive, it is understood from the name itself what each of the events are: internal, send and receive. You can also have an example where suppose P1 is a process P1, it will calculate salary and send salary to P2. P2 will receive salary and print the salary. So what are the events inside? That there will be an internal, okay, how it works, the workflow of the events is there will be an internal event, it will be sent, received to the other internal one. That is how it works. That is model of distributed execution. Then we can learn this in detail with the help of space-time diagram. But before that, you need to know what local state and global state is. We have already studied this, but I'll just give you a revision of it. Local state is, we know each process will be having registers, variables, stack, memory and all. That is called local state. For example, we are taking P1 is a process P, there is a process P1 and it is having a count of 15 and balance will be 800. So this is some information which is available only inside or which belongs only to P1. That is local state. Now what about global state? Global state means it is the sum of all the local state and messages in transit, or the processes plus communication channel, you can say. For example, you are having a process P1 and the balance of P1 is 5,000 rupees and P2's balance is 3,000, and then there is a transfer happening between them, rupees 1,000 transfer is traveling. So global state, what all will it contain? It will contain P1 state, that 5,000 will be there, and P2 state, that is 3,000, and the message in transit, how much? That 1,000. That is also an amount, it will not be deleted. Now why is this global state important? Because if the system crashes, how do we recover? We must know what each of the process was doing, or if there was any message still traveling. And we also have to learn about Chandy-Lambert's snapshot algorithm. We'll record this global state, we'll study that in the upcoming modules. Then we have a space-time diagram, which is there in the next slides. I'll just give you an intro about what it is. It is the most important concept of this module, space-time diagram, and here almost every future algorithm uses this diagram. We'll be explaining that in detail, okay? But before that, I just want you to know, here we have, just focus on the slide. Here we have a process Pi and there is an event called X. So what is E? E is the event of process Pi. Why do we write EIX? Here I is the process number and X is the number of X is the Xth event, the number of event. And if we are taking a message called M, if we are sending sending a message, we'll write send of M, and when it's received, it will be denoted as receive of M. That's just the denotation. I just want you to know that. Then we are coming to the next part, where you should know that all the events in a process, when we are taking the events, it will be linearly ordered. How? It will only come, first event 1 will occur, then event 2 will occur, then event 3 will occur, etc. In a process, we cannot tell first an event 3 occurs, then event 1 occurs. We cannot tell like that. It will just go in that linear order itself. And HI is the set of events which is produced by process Pi. And this relation is it expresses causal dependencies, which we will be learning. Okay, this is our space-time diagram. As you can see here, this is used to represent the distributed execution. As I told you before, you can see P1, P2, P3. These are the processes, each of the processes, and in each of those processes, you can see there is an event. First event 1 will occur. Look at process P1. The first an event 1 will occur, then event 2 will occur. Why E11? The first one, the one below E, is of the process. It denotes this event occurs in process P1, and the one Above the E, the superscript will be denoting the number of event E11, E12, E13. So only after E1 occurs, E2 will occur. You can see it is moving in a linear order. Okay, the time increases as we move towards the right. Okay, that is about space-time diagram. From this figure itself, we can understand who sent first, who replied first, when communication happened, and all those things. And why this diagram is important, because without it, understanding distributed algorithm is almost impossible, and it will help us understand message ordering, causality, logical clocks, snapshots, and all those things. Okay, so far what all did we learn? We'll just go with a quick revision. We have distributed program, that is program splits across multiple computers. Distributed execution is the running of distributed programs. Event is any action performed by a process. Local state is state of one process. Global state is all the process state plus what is inside channel state. Space-time diagram is a graphical representation of execution. I hope that much is clear. Then we have to know about happened before. I'll just give you an example for that. Imagine you're chatting on WhatsApp, you send happy birthday to your friend. It's your friend's birthday, you're sending happy birthday, and your friend replies, thank you. Now, which message came first? Obviously, happy birthday. And that reply on the birthday wish was thank you. This dependency is called causality. Only because you send the happy birthday, your friend send back to you thank you. Another example, that is a basic example. I hope you understood from that as well. I'll just give you another example of a process also. There is a process P1 sending 500 rupees to process P2. Now, the process P2 will receive the rupees 500 and that will be deposited. That money will be deposited. Now, is it possible for P2 to deposit the money before receiving it? No, it is not possible. And the receive event depends on the send event. The receive event depends on the send event. That is called causal relationship. The dependency is called causality, and the event which depends on the send, the receive event which depends on the send event is called causal relationship. And then we have happened before relation. Now, this was introduced by Leslie Lamport and it is written as, so there somewhere over here. Okay, so it is over here. You can see, just look at the figure over there in the box. Yeah, it is over here. We have causal dependency denoted as that arrow you can see, right? That is happened before. It is read as event. If there is an event, there is no, okay, here if we have EIX and EJY. So we can say that event EIX happened before event JY. That means the second event EJY could not have happened without the first event happening. So first event should happen, only then second one will happen. For that we have three rules which you should be knowing, called same process rule, message rule and transitive rule. I'll just give an intro about what it is. Same process rule means if two events occur in the same process, the earlier event happened before the later event. That is in process P1, event 1 occurs, then event 2 occurs, and after that event 3 occurs. So I can write event 1 occurs and then event 2 occurs. First event 2 occurs, then event 3 occurs. In that case, I can write event 1 occurs and only then event 3 occurs. So that is simple, just the events follow the execution order. Then the second rule is message rule. That is, if P1 send a message M to the network and P2 receive it, then I can write send message first and receive message second. A message must be sent before it can be received. That is message rule. Then we have transitive rule. Suppose A to B, A is moving to B and B happens before C, then A happens before C, just like before, exactly like maths. Example, first you wake up, you brush, you go to college, then what does it mean? Only if you wake up, you will go to college, something like that. Okay, that is about the causal precedence relation. Okay, that's related to happen before relation. Yep. And this is what I've just told you about transitivity and those things. Now we have causal precedence relation. But before that, you need to know what concurrent events are. Imagine process P1 calculating salary and process P2 will have to print the report. Neither of these process communicates and neither depends on the other. Which happens first? We do not know which one will happen. Maybe P1 will happen, maybe P2 will happen first. Maybe both of them will be together. So it is happening, it is going somewhat in parallel. That is concurrent events. We do not know which one will happen first. Do not think concurrent is same time. Concurrent means there is no causal relationship between them. They can occur at different real times, but it does not influence on other. That is causal precedence relation. Then we have physical concurrency and logical concurrency. These are two ways to say that two events happened at the same time. Physical concurrency is real time. That is what we normally think of. That is, two events occurs at exactly the same instant according to a physical clock. Imagine two students are there. They clap exactly at 10 a.m. The clock will be 10 a.m. Student A clap and student B will clap. Since they happened at the same clock, they are physically concurrent. We are having a same clock. That is why we can say it is physically concurrent. Logical concurrency is related to the distributed system. We know distributed systems don't have a common clock. So instead of asking did these events happen at the same time, we ask did one event influence the other. If the answer is no, that means they are logically concurrent. So computer A calculates salary, computer B print report like the previous one. Here no messages are exchanged. Neither of them depends on each other. So they are logically concurrent, we can say like that. Then you need not get confused between two logically concurrent events, because the two logically concurrent event may not occur at the same instant in physical time. Please keep that in mind. Okay. I'll give you one simple example of two people to make this more understandable. There are two people, Alice and Bob. Alice is making tea in Kerala and Bob is writing a report in Delhi. Okay, that is an example. Did Alice's tea making affect Bob's report? No. Suppose Alice starts at 9 a.m. and Bob starts at 10 a.m. Next day, Bob will start at 9 a.m. and Alice will start at 9 a.m. Or maybe both of them will start at 9 a.m. Does this final outcome change? Does the final outcome change? No, because the two activities are independent. They are not dependent on each other. That is logical concurrency. Whether logically concurrent events coincide in physical time or occur in different orders does not change the outcome of the computation. If events are independent, their actual clock time doesn't matter. Only the causal relationship matter. That is physical and logical concurrency. Physical concurrency is based on clock time and logical concurrency is based on causality. The physical concurrency, events occurs at the same time and requires synchronized clocks, whereas in logical concurrency, events do not affect each other and no synchronized clocks are needed. Physical concurrency, it is difficult in distributed system. Why? Because they do not have a common clock, right? And it is concerned with when. Whereas in logical concurrency is where what is used in distributed system and it is concerned with dependency. So logical concurrency, two events are logically concurrent if neither event causally affect the other. Their physical execution time or order does not affect the outcome of the computation. Whereas in physical concurrency, two events are physically concurrent if they occur at the same instant according to physical time. Okay, distributed systems care about logical time, not physical time, because there is no global clock. Therefore, causality is more important than actual clock time. Always keep that in mind. Next, in the next video, we'll be learning about models of communication network. So, till then, bye bye.